All right, hopefully that last video blew your mind where the derivative of e to the x is itself. That's just absolutely amazing. So let's move forward and talk about the derivative of exponential functions with a base other than e, and then start doing some actual examples of finding derivatives. All right, so to find the derivative of an exponential function with a base other than e, do you want to start that whole limit definition process again? Nah, I don't really want to either. And so that's the whole point of starting with the base e, because now we can actually do some nice properties that we studied back in the exponential and logarithm topic. So we're going to use that change of base theorem to rewrite something of a to the x as, and remember that if you wanted to rewrite using the change of base theorem, you can write a or any base to the x as e, rewrite it as e to the ln a x all up there. Okay, so this is really, really nice because now we can actually just use the result that we just proved and then find the derivative very quickly. So for any positive constant, a not equal to 1, we would have the derivative of a to the x is going to be the derivative of that reworked version with the change of base theorem. And then the derivative of e to the, and we have to be a little careful because this is not just e to the x. This is e to the ln a x. And remember, ln a, that's just some number. Okay, we're letting a be a constant, so this is just some number times x. So if we have the derivative of e to the something times x, the result that we just got is, it should be itself. Okay, but then what is this times ln a? Okay, well, the extra ln a comes from the chain rule. Okay, so in the last section, we developed that chain rule. So remember, this derivative here, e to the x is itself, but if you've got e to the power of a different function besides just x, where this ln a is technically a constant times x. So this is kind of like e to the u, where u is a function of x. So it's going to be itself times the derivative of u. And the derivative of it, like ln a, that's just a constant, remember. So if this was like a 3x up there, then it would just be 3. Okay, so that comes from the chain rule, and then we usually just put the number in the front. Okay, so yeah, chain rule, very important to keep track of that chain rule. Okay, so the derivative of e to the x is itself, but the derivative of e raised to some stuff is going to be all of itself with the stuff up there, and then times the derivative of the stuff. Okay, so we'll do plenty of examples, but I want to just box that result right there. We didn't need to do that whole limit definition process because we already did it for e to the x. So the derivative of a to the x is just going to be ln a times a to the x. So still a pretty nice result, but we get this extra ln a that pops out from that chain rule. And so I want to really make a note of that. It's important to keep in mind the chain rule from now on. So if u is a function of x, okay, so it's like u of x equals, and then whatever expression it has with x involved, and du is the derivative of u with respect to x, then the derivative rules that we just developed can be generalized as the derivative of e to the u is going to be e to the u times du. So e to the stuff equals all of itself with all of that stuff up there times the derivative of the stuff. Okay, and then the derivative of a to the u is going to be natural log of a times a to the u, so all of that stuff still up there, and then times the derivative of the stuff. Okay, and so as we're developing all kinds of derivative rules, a lot of times if you've got like a table of derivative rules, you see a lot of this little times du on the outside of all of them, and that's just to remind you of the chain rule. And it's really easy to forget, and that's one of the most common mistakes when finding derivatives is people tend to forget the chain rule if there's more than just x involved. All right, so let's go ahead and do example 1 here. Let's find the derivatives of each function. So f of x equals e to the x squared. So this is a chain rule, technically, because we've got e to the u. So the way I want to write this is it's going to be f prime of x is, and the way that it works is it's going to be itself, okay, e to the u, it's just going to be itself, all of the stuff, times du, so times the derivative of x squared, so that's times 2x. Okay, another common mistake that I see is a lot of people will just put e to the x for the first part. Okay, but if it's starting with e to the more than x, then you have to include all of that stuff that's more than x up there. Okay, so a lot of times we write the extra stuff in the front like this, just looks a little bit nicer. Okay, part B, s equals 3 to the power of t. All right, well, we've got different letters involved, so let's just go ahead and write it as ds dt equals, so 3 to the power of t, okay, so that's just going to be ln of 3 times 3 to the power of t. Okay, no chain rule needed there because it's just t. But if you wanted to think about the chain rule, what's the derivative? If we were going to go times du, what's the derivative of just t? It would just be times 1. Okay, so interesting. The chain rule is kind of always there, but if it's not a separate function, then it's just times 1. It's just times the variable, the derivative of the variable. So kind of interesting. The chain rule is always there. Okay, let's proceed. Part C, g of x equals that. Okay, so 8e to the power of e to the power of x. All right, so this is a little weird. Let's write this out as g prime of x equals. Okay, so this is 8e to the stuff. Okay, so it's like that's the stuff. So the derivative of e to the stuff is itself, including the constant. Okay, so that's itself. And then times the derivative of the stuff. So the derivative of e to the x up there is just e to the x, right? Okay, and then there's not really a whole lot of different ways that we can clean that up, unless you wanted to get a little bit fancy with power rules. Perhaps we could get a little bit fancy with power rules where the 8 would stay there. E is the base both times, and remember that if you've got a base times a base, the powers add. So it would be the power of e to the x up there could add with that power of x right there. So not really necessary, but that can be rewritten in this form. Okay, kind of weird, kind of fancy, but yeah, that's e to the power of stuff. So it's going to be itself times the derivative of the stuff. Okay, kind of interesting. Okay, for part D here, let's see, y equals, so let's go ahead and write this as dy dx. Okay, so for dy dx, now we've got 4 times this 2 to the 1 over x thing. So we're definitely going to have some weird situations going on. So let's see, the 4 is just going to have to stay alone because that's a constant times a function. Okay, and now let's be really, really careful. We have the situation of a to the power of u. So the derivative of a to the power of u is going to be natural log of, and I'm going to use extra parentheses here, natural log of the base times the stuff itself, okay, a to the u itself, so it's going to be 2 to the 1 over x, and then times du, okay, because this is definitely a chain rule, 1 over x is some extra function, so times the derivative of 1 over x, okay? What's the derivative of 1 over x? Okay, you can go ahead and just use the power rule on that. So maybe some scratch work. Note that 1 over x is the same as x to the negative 1. And so if we wanted to do the derivative of x to the negative 1, don't forget these old derivative properties. That's going to be power rule, negative x, and then reduce the power by 1. So that's negative 1 over x squared. So doesn't hurt to do some scratch work if you forget how to do derivatives of old stuff like that. Okay, so again, that's natural log of a times a to the u, and now we're doing times du. And so we're finding the derivative of that 1 over x thing. And so that came out negative 1 over x squared. Okay, a little bit more involved there. Let's go ahead and clean this up. Probably not a whole lot of stuff that we can do, but let's clean it up a little bit. 4, don't multiply the 4 with that 2 right there because that 2 is being raised to the 1 over x power. So maybe the only real way to clean this up is I'll just use this negative that's involved over there with the 4. So let's write this as -4. And then we've got ln of that 2. And then this has 2 to the 1 over x. None of that stuff can be combined because the 4 is multiplying like a regular 4. That 2 is inside the natural log. And then that other 2 is being raised to a power. So none of that can be combined. And then let's just go ahead and write the x squared with its own fraction on the bottom there. So then this would be the answer. Okay, yeah, a little weird. That chain rule, it really ends up being the part that most mistakes come from. All right. Yeah, I'll make a separate video to pick up on example 2.